Welcome to 29th lecture of graph theory. In the last class we were looking at this theorem, every graph G with at least 3 vertices and the vertex connectivity kappa greater than the stability number, the independence number, the cardinality of the biggest independent set, then it has a Hamiltonian cycle. So, we told that if the independent set is small, say if it is less than equal to t, then that there is an n by t cycle, length cycle is there in the graph is obvious, but if the independent set size is less than the connectivity, then we can be sure that there is Hamiltonian cycle. This is the proof we were trying to do the proof for that. What we did is to take a longest cycle in the graph, So, right. So, now when you look the longest cycle you took, so you can assume that alpha is so of case. So, what will happen, for instance, the connectivity can be assumed to be 2, then of course there is a cycle. So, we can take that and then now we see, suppose this longest cycle is a Hamiltonian cycle, is of length n, then there is nothing to prove. Therefore, we can assume that there is at least one vertex outside this, and because the connectivity is k, there should be a fan starting from this vertex to this cycle. The fan means there is some paths of this sort, right, some paths of this sort. So, how many fans can be there? So, it is equal to the connectivity. The fans means it starts from here and then goes through these paths and ends exactly in one vertex here. See, these are the end of the fan paths, and they will hit this cycle in only exactly one point. In fact, the first time it hits the cycle, it stops. It is not that you can have 2 cycles from one path, 2 vertices from the cycle on the same path, and they are all disjoint paths except the beginning point. Now, we notice that the cycle length has to be greater than or equal to strictly greater than kappa, the connectivity, because if not, then you can get paths like this to all of them. In fact, see, it is not even necessary to get paths to all these vertices on the cycle, but even if you can identify 2 vertices on the cycle which are adjacent in the cycle and 2 fan paths ending it is like this 2 green vertices, then we can easily see that there is a contradiction, because if you travel like this and then go like this and then come back like this, you will get a longer cycle than the blue cycle that we have drawn here. So, this black cycle, I have dotted black cycle here, is longer than the blue cycle, because there is at least one more vertex in that. There can be several vertices also, because here also we can have intermediate vertices, but even if they are not there, it means that we have one more vertex at least. So, it will be a longer path. So, we can assume that it is not possible for the fan paths to end in consecutive vertices, that means adjacent vertices on the cycle. So, it means that C has to be at least 2 times kappa, because you know those we can identify all those paths, kappa paths, right, and then at least one vertex has to be left in between. So, the currently the picture that we see is like this. So, this blue cycle, yeah, and this paths from this vertex will come here. Suppose it hits here, then it won't hit in the next one, right, there won't be one an edge, then it can hit here, and then it cannot hit here. So, it can hit here, and then another path can come and hit here. So, like that, right, another path can come and hit here, but if it hits here, then there should be some other node here, right. Okay. So, the point is, if a node here is the n vertex of a fan path, then this vertex and this vertex, the adjacent vertices cannot be the n vertices of a fan path. Moreover, in fact, it cannot be directly connected to. So, this edges cannot be there at all, right. For instance, this kind of edges cannot be there at all. They are not neighbors of this vertex. These fan paths are not there. It means that they cannot be the neighbors of it also, because if there is an edge between them, there is a fan path, right. So, now what we are going to do is to demonstrate independent set of cardinality at least kappa plus 1. We know by our assumption alpha is less than equal to kappa. So, if you show that there exists an independent set with cardinality kappa plus 1, this will violate this assumption, and then we get the contradiction. So, our candidate vertices are this alternate vertices, this vertices which are just after the endpoints of these fan paths, the endpoints of these fan paths on this cycle. So, those vertices will form a form an independent set. And see, and we, because there are these kappa fan paths, there are kappa of them, and then this along with that we will take this outside vertex also. So, together they will form a k plus 1 independent set. That is what we want to say. So, now again we will repeat this. So, the picture now is, so we have this cycle and this outside vertex, the fan paths are coming and ending at points, several points, say these are some other points where the fan path ends, and then we can mark these points, the points just on two sides of the just after, and it is a, you can go in a clockwise direction and then mark the anti-clockwise direction and mark the paths. These are blackened vertices are the vertices which is just after red vertex. Red vertex is the end point of some fan path, okay, like this. Now, we pointed out that these black vertices are non-adjacent to this vertex. So, I will say these vertices are non-adjacent to this vertex, because if there is a direct edge to that, then we can in fact get a longer cycle than this cycle, because our assumption is that was the longest cycle. If you are getting a longer cycle, then it is a contradiction. Now, suppose these black vertices were forming an independent set, then along with this black vertices I can add this also, because this is non-adjacent to all of them, and clearly these are at least kappa of them. So, we will get kappa plus 1 independent set, sized independent set. To do this thing, so we see what, suppose there is an edge between two such vertices. For instance, suppose this edge is there, right, here between these two vertices. So, we will show that such an edge cannot exist. That is why we claim that they are independent, this black vertices. Suppose it is there, then what can happen? The point is that, see, this is a red vertex, right, and then sorry, this is a red vertex, this comes after that, and here this is also a red vertex, this comes after that, right. Now I will show a path which is which is bigger than, okay. So, here we draw like this. So, for clarity sake, we will draw a figure. I mark the red vertex here, and then I mark another red vertex here, and then I mark one black vertex here, and I mark one black vertex here. Now, suppose this connection is there here, right. So, maybe this blue connection is there here, sorry, this green connection is there here. Now, you consider this outside vertex, we will show how to get a bigger cycle including that, right. Here we have this connection, this is a path here, it can be, so there is a path here, right. Now, how will I get a bigger cycle? So, the point is, I am just using this violet color to track the path. We will start from here. So, then we will go like this, and then here we will take this turn, and then here we will take this turn, and then go back here, and we will do the cycle. So, we have touched this cycle has touched all the vertices of the old cycle and also included this new vertex. Therefore, this is a bigger cycle, it is a contradiction to the assumption that the old one was the longest cycle. See, what edges will go away from here is this one, and this one also will go away from this. It will look like this, right. So, earlier this was the cycle. Now, we removed these two edges, and then we using this connection we could complete the cycle like this, including the outer vertex, that was the trick. So, therefore, what we have shown is this kind of an edge is not possible, because between the two black vertices here we cannot have an edge. That means, the black vertices, that is the vertices which are just after the red vertices in a counterclockwise order, are indeed independent set, and those black vertices are at least kappa of them, because there are at least kappa red vertices, because the fan has at least kappa paths, the connectivity, vertex connectivity number of paths in it. So, those many black vertices will come, plus this vertex will form kappa plus 1 sized independent set, that is the thing. So, therefore, it is a contradiction to the assumption that alpha was less than or equal to kappa, right. So, it contradicted that. So, we claim that. So, where is the contradiction coming from? The contradiction is coming from the fact that we, after taking the longest cycle, we could find some vertex outside which is not covered by that. So, the longest cycle has to be such that it covers all the vertices, that means it has to be a Hamiltonian cycle itself. So, this should be a Hamiltonian cycle in the graph if alpha is less than or equal to kappa. This is the kappa being the vertex connectivity. This is statement. Now, the next theorem about Hamiltonian cycles that we want to study is the following. So, this is about how the degrees of the, see as we have seen, the Dirac's theorem said if the degree of a graph is the minimum degree of the graph is greater than equal to n by 2, then there is a see if it is strictly greater than n by 2, then there is a Hamiltonian cycle, right. So, now that is a condition on the degrees of the vertices. So, this was in fact several researchers have worked improving the result of Dirac, like relaxing the degree condition more and more and more, and then finally we came to this particular result of Chvatal, and which makes use of a property of the degree sequences to say that the Hamiltonian, whether there exists a Hamiltonian path in the graph or not, right. So, this is it's only again the condition will say that if the degree sequence satisfies a certain property, then there will be a Hamiltonian cycle. So, for that we need some definition, and first of all, what is a degree sequence? What is the degree sequence? So, the given any graph, you can write down the degrees of it. So, for instance, for this graph, see for this graph, so the degree of this vertex is 1, the degree, see I will write the degrees here, degree of this vertex is 1, degree of this vertex is 3, here is again 3, here is again 3, this is 2, 2. So, degree sequence is written like this 1, 2, 2, 3, 3. These numbers are written in the increasing order, that is all, with the repetitions, right. Some numbers are repeating more than once, we will write them once again. For instance, so can you imagine a graph with the degree sequence like this? Of course, it is this graph. So, 1, 2, 3, 4, 5, 6. See if one more 2 is there, that is the cycle, right. So, see for instance, for this graph, star graph, what will be the degree sequence? It will be 1, 1, 1, 1, so n minus 1, right, because the last one will be n minus 1, until then it will be all ones. So, this is what the degree sequence of a graph is. So, what we write down the degrees and then order them, right, in the non decreasing order. So, this is degree sequence, this is the degree sequence of a graph. Now, suppose we are given a degree sequence. So, say suppose we are given a degree sequence A1, A2, A3, so n numbers will be there, some of them may be repeating, and we say that another degree sequence D1, D2, D3, Dn is pointwise greater than this degree sequence A, the first degree sequence. So, if this for each I, AI is less than equal to Di. In other words, this is bigger than or equal to, this is bigger than or equal to, this is like that. So, in each position, each position the number here is at least as big as the number here, then it is pointwise greater, right. So, now we say that the degree sequence is pointwise. See, suppose, so we are given a degree sequence A1, A2, An. So, we say that it is a Hamiltonian degree sequence if any graph with that degree sequence or any other degree sequence which is pointwise greater than this is Hamiltonian. So, which means that so when do I say that this degree sequence is Hamiltonian? So, not only that any graph with this degree sequence is Hamiltonian, also we need any graph with the degree sequence this having all the values at least as much as the corresponding values in this also to be Hamiltonian, right. The degree sequence and all the point wise degree sequences of it should correspond to graphs or the graphs with such degree sequences should all be Hamiltonian. Then we will say that this degree sequence is Hamiltonian. In other words, it is in those numbers the Hamiltonicity is inevitable if the degrees are those numbers or higher. So, we will get the Hamiltonian cycle, right. So, now we will characterize the degree sequences which are Hamiltonian, that is the next intention. So, we will say that an integer sequence a1, a2, an such that, so this is an increasing non decreasing sequence. So, of course, the biggest number is strictly less than n, so the lowest number can be 0 and number of vertices is assumed to be always greater than or equal to 0, otherwise there is no cycle. So, such a degree sequence is Hamiltonian if and only if the following holds for every I less than n by 2. What is the condition? If a I is less than equal to I, then we should have a n minus I greater than equal to n minus I. So, this requires some kind of, this condition is a little tricky. So, what is this saying? So, it is saying that, suppose this is the degree sequence a1, a2, a3, n minus 3, a n minus 2, a n minus 1, a n. See, we have an n by 2 here somewhere. For all I strictly less than n by 2. So, if you are picking up some I before this can be, if it is an odd number up to n by 2 floor, if it is an even number up to n by 2 minus 1, right. So, you take any value here and suppose I take this one a3 and then ask, is a3 less than equal to 3? This is the question you are asking. The third number, is the third number less than equal to 3? That is what it is asking, right. In that case, suppose it is, if it is not less than equal to 3, then there is nothing to bother about, but suppose it is less than equal to 3, then we should get the corresponding number n minus 3. N minus 3 is not the third number from here, it is actually the fourth number from here. It is essentially, there is a, it is not symmetric when you are looking at the third here, this is the fourth from this side. So, therefore, but we are matching this for this. So, we want a n minus 3 should be greater than or equal to n minus 3. This is the condition we need, which essentially means that the number here has to be at least n minus 3. So, this also will be at least n minus 3, this also will be at least n minus, because this is an increasing order. So, therefore, we will, if the third number is at most 3, then we will have in the end 4 numbers which are at least n minus 3, right. This one, this one, this one and this one, fourth. In general, so you will take the ith number here, of course, I has to be strictly less than n by 2, and if it so happens that a I is less than equal to I, if it is not less than equal to I, if it is greater than I, forget about it, we do not have anything to worry about. But suppose this condition is met, then we should have, so we count from this side the I plus 1th number, that namely a n minus I has to be such that greater than or equal, that is greater than equal to n minus I. In other words, here we should find at least I plus 1 numbers which are greater than n minus I. If we have here at least I numbers which are less than equal to I, because here all these things will be less than I, right. If a I is less than equal to I, at least I numbers less than equal to I, then we should have at least I plus 1 numbers greater than or equal to n minus I. This is the condition. This is slight asymmetry there, and that is not I, but I and I plus 1. This is what the condition says, right. Now, we will show that if this condition is met, then every one of the sequences which is pointwise greater than this sequence itself, or any sequence which is pointwise greater than this, should corresponds to graphs which are Hamiltonian. Or in other words, if a graph has a degree sequence which is either this or a degree sequence with which is pointwise greater than this, that graph has to be Hamiltonian, because this satisfies this condition, right. This is what we are going to tell. See, the interesting thing is, so yeah, this satisfies the condition. Suppose you consider a pointwise greater degree sequence, will it also satisfy the condition? So, of course, that will satisfy the condition, because you know, if you take any ith vertex, sorry, ai here. So, suppose you consider di instead of this, a pointwise greater degree sequence. If this di has become greater than ai, well and good, we do not have to worry anything about, because it does not, we are not asked whether this condition anyway says if this is true, then this should be true. If this is not true, then we do not have to worry about anything. Suppose on the other hand, if di is also less than or equal to I, right, then we just need all of the n dn minus 1 up to dn minus I, all of them should be greater than or equal to n minus I. That will anyway be true, because anyway all of this dn minus 1 up to dn minus might have increased their value, not decreased. Therefore, we still will have so many values which is of greater than or equal to n minus I. So, this will be met even for if this is met for an integer sequence, any pointwise integer sequence also will satisfy the condition. So, therefore, that will not be lost if you consider a pointwise greater integer sequence, right. So, now the idea here is to show first. So, what is our intention? We will show that if a particular degree sequence satisfies this condition, then any degree sequence which is pointwise greater than or equal to this will be such that if a graph has that degree sequence, then it will be Hamiltonian. This is what we want. Suppose this is not true. Suppose this is not true. That means, so you have this degree sequence A1, A2, A3, so an, which satisfies our condition, that is for all I less than n by 2, ai less than equal to I implies an minus I greater than equal to n minus I. Then in that case, so if something is wrong, so that means there can be, suppose there is another degree sequence, not necessarily this, some pointwise greater degree sequence like d1, d2, dn, such that a graph corresponding to it, some g corresponding to this degree sequence is not Hamiltonian. Suppose it does not have the Hamiltonicity. Now, what we are going to do is to find one such degree sequence which is very suitable for us to work with. What will we do? We will consider all degree sequence which is pointwise greater than this and does not satisfy the theorem. That means, it is not Hamiltonian, because once it is pointwise greater, of course this condition will be met, but suppose it is not Hamiltonian. We will pick up that degree sequence and a graph corresponding to that. So, such that it is of the maximum number of edges possible. Among all the possible degree sequences which are pointwise greater than the given degree sequence A1, A2, A3, An, we will pick up the one such that the corresponding graph has the maximum possible number of edges. That means, if you consider adding one more edge to it, it will satisfy, it will have a Hamiltonian cycle. Why? Because if you add one more edge to it, its degrees will increase. So, when the degrees increases, the degree sequence, if the degrees are only increasing, you may rearrange the degrees, but of course, it is very clear that it will be pointwise greater than the old degree sequence, because some degrees increase, that is all. They may go to a higher place, but what takes the current position will be definitely some bigger number than what it was earlier, right. So, when we rearrange the numbers after making this change. So therefore, so that will be, if you add one more edge to such a graph, it's clear that such a graph will be somewhat saturated, in the sense that if you add one more edge, it's maximal, in the sense that if you add one more edge, then immediately the Hamiltonian cycle will appear. So, it's about to become Hamiltonian. It's just a very saturated, very extreme situation. That means, any more edge will make it Hamiltonian, right. That is the type of graphs G's. That is why we are taking a graph with maximum number of edges, which among all the possible violations, I mean among all the possible graphs which does not have Hamiltonian cycle and having a degree sequence pointwise greater than the given degree sequence, right. So therefore, if you add one more edge, the degree sequence of the new graph also will be pointwise greater than this, and then if still there is no Hamiltonian cycle, we could have as well taken that, right, because we went for the biggest number of edges among all the possible violations, the bad examples, right, which does not satisfy the theorem, right. So, then so we pick up that graph, let us say G is that, and the corresponding degree sequence can be written, say let us say D1, D2, D3, Dn is the degree sequence. And as we have already noticed, this pointwise degree sequence compared to the original degree sequence given, and also because this original sequence satisfies that condition, that means Ai less than equal to I implies An minus I greater than equal to n minus for all I. This sequence also will satisfy that, that means for all I less than n by 2, if di less than equal to I, then it will imply that dn minus I greater than or equal to n minus I. So, this is the this condition also will be met. If this satisfies this also will be satisfying, because I already explained why it is, because everything is only increasing. If this is not satisfied, well and good. If this itself is not satisfied, well and good, but if it is say still satisfying even after the increase in this thing, and it is very clear that all these numbers n minus I has only increased. So, this is not changing, therefore, this will still satisfy, right. So, that is the thing. Now, this is the graph. So, you can always add any edge and Hamiltonian cycle will appear. In other words, if you take any x, y in G such that it is non-adjacent, there should be a Hamiltonian path already between this x and y, right. That is why when you add this new edge, you get a Hamiltonian cycle, otherwise how can you get it. So, between any pair of non-adjacent edges, you should already have a Hamiltonian path ready. So, therefore, when you add a new edge, it will become a Hamiltonian cycle. Now, let us consider an x y. So, an interesting thing is the question we will ask is that, so there is a Hamiltonian path between x and y here, we know that. So, is it possible that we can get a Hamiltonian cycle immediately from that? For instance, when we studied the Dirac's theorem and we considered the proof of that, we had seen that if we considered these vertices, right. So, these are the neighboring vertices of x. Suppose these are the neighboring vertices of x, and then we consider the vertices which are just behind the neighboring vertices of x. This violet vertices which I have marked just behind it. So, here suppose you have these vertices, one of them, if even one of them is adjacent to y, if one of them is adjacent to y, then we can convert this Hamiltonian path into a Hamiltonian cycle. How do we do that? That is by that is by, so this is the path, of course, this was the path. This was the path. So, then this, suppose if this was adjacent to this, even one of them, and then we can delete this edge, we can break here, and then what can we do? So, here you see there is a connection between this and this, I am marking it here, and then we can follow like this and then come back through this edge, and then we can go here, right. So, we will complete the cycle here. What the only thing that we have done is to remove this this portion, right, this particular, sorry. So, this connection is there, this connection is there. So, we just cut this edge, and then making use of the fact that there is a connection like this and there is a connection like this, we could complete the cycle, right. So, what we see is none of it means that if we do not have a Hamiltonian cycle in the graph, none of the vertices which are just behind a neighbor of x can be a neighbor of y, right. So, in other words, again this is x, this is y, x and y is any arbitrary any pair of non-adjacent vertices, and if you consider the red vertices as the neighbors of x, if you consider the red vertices as the neighbors of x, and then let this orange vertices be the vertices which are just behind the red vertices. It does not mean that, see, this orange cannot be red, there can be, it can be red and orange together, but in that case there will be one more orange behind this, that is all. We are just considering the vertices which are just behind the neighbors of x, right, and none of these orange vertices can be then the neighbors of y. So, if you count the orange vertices, there how many of them are there? There are dx of them, right, dx of them, because for each neighbor of x we will get one behind. So, dx of them, and then the none of those vertices are taken by the neighbors of are neighbors of y. Therefore, those neighbors of y, as we know, because this is a Hamiltonian path, all the neighbors of y also should be present in this path only, they should sit somewhere, right, in the path, not on this orange marked vertices, but somewhere else. So, but then they will get only the remaining n minus 1 minus dx positions, right, because these dx's are all from here to here, because the y cannot be anyway, because there is nothing beyond y. So, this one of these orange vertices cannot be y itself. So, we have n minus 1 vertices in here, and then y's neighbors also has to be in this thing. So, if you add dx plus d of y, this has to be at most n minus 1, right, is not it, at most n minus 1. This has to be at most n minus 1, because otherwise this orange, some of the orange vertices should be a neighbor of y, they can't be if this is not true. So, if together they make more than n minus 1, that means they will have to share, right, they cannot be disjoint. So, then we will get that situation where this is connected to this and this is connected to this, and then we can break here and then we can break here, and then we will get a cycle jumping here and then like this and then like this, we will get a Hamiltonian cycle. That is a contradiction. We know that the graph does not have a Hamiltonian circuit. So, for every non-adjacent pair we have this property also, right. This is remembering how Dirac did his original proof. We see that this is dx plus dy is less than equal to n minus 1 is true for every non-adjacent pair, because there is already a Hamiltonian cycle between Hamiltonian path between any non-adjacent pair x and y. Now, see, somehow we want to find out a contradiction, somehow we want to find out a contradiction. So, what would be some place, suppose we will search for some x and y, some pair x and y, non-adjacent pair x and y, such that this gets violated. So, it is very natural to this gets violated, or it will create some trouble somewhere. So, it is very natural, because this saying that this plus this has to be less than equal to 1, it is very natural to seek that pair of x and y where dx plus dy is maximized, because if it is maximum, maybe there is a chance that it will go beyond n minus 1, right, because the biggest x and y such that dx plus dy maximizes is a good candidate. So, we will go for that. So, let x and y be selected such that this is x, this is y, let such that among all the non-adjacent pairs dx plus dy is maximum for this pair, maximum for this x and y, right, this is maximized. Now, of course, we know dx plus dy is indeed less than equal to n minus 1, otherwise we will already have a Hamiltonian cycle, right. Now, we will see what the condition, Chvatal's condition, can say about this vertices, right. Now, so the point here is, if you consider the smaller of these two things, dx and dy, because it is at most together they are at most n minus 1, the smaller of them has to be strictly less than n by 2, is not it, because if both of them are at least n by 2, then together they will make n. So, the smaller of dx and dy has to be at least n minus 1. So, let without loss of generality, let us say x is the smaller the vertex with the smaller degree, and then dx is less than n by 2. Now, dx has to satisfy the let us see whether dx will satisfy the Chvatal condition or not. That is what we want, right, because if dx satisfy the Chvatal condition, suppose somehow dx satisfy the Chvatal condition, then we will have dx, suppose put dx equal to some h, then we will see the h, right. So, the position dx when dx comes, right. So, that number, so this vertices will suppose this position yeah. So, we will get some condition from this thing, right. Now, let us see the if so this, so what we can do is we will look at the x, and in the sequence, in the Hamiltonian path, we have seen x and this we have seen y. So, remember that we had this path, and then so we had marked certain orange vertices. So, let us say let us draw the path using black, and then we had marked again. So, we had drawn the path using this is x and this is y. This is x and this is y, and then this is the Hamiltonian path. So, let us say these were the neighbors of x, some neighbors of x, and we had marked these orange vertices which are just behind the neighbors of x, right. And we had already noticed that this kind of edges cannot be present, right, because if this edge was present, then along with this edge it would form a Hamiltonian cycle like this, right. This we have already seen. Therefore, this kind of edges will never be present. In other words, this orange vertices, each of these orange vertices along with y. So, if I call it say x1, this is x2, this is x3, right, and this is xh, where h equal to d of x, right. Each of these x1 to xh are candidates to become candidate for a non-adjacent pair along with y, because any xi y pair is a non-adjacent pair. So, we could have considered that. So, we could have taken the degree of dxi, considered the degree of dx plus y di instead of dx plus dy, but we saw that this x and y was selected such that dx plus dy sum was maximized. So, what can we tell about this? This sum is definitely smaller than or equal to this sum for every I, for I equal to 1 to dx, that is true, right, 1 to dx means h. So, all of them, if any of these vertices, if I consider, if I sum the degree of this plus the degree of this thing, that should be less than the degree of this plus degree of this. Otherwise, we would have taken that pair instead of x and y, right, y and that see xi would have been taken. So, immediately, because dy being the same here, we can say that this has to be smaller than or equal to this. So, each of these vertices xi has to be smaller than equal to the corresponding vertex x. So, we see this, it is clear for one of these vertices x1, x2, x3. See, this vertex may even be x. So, let us say, so therefore, do not worry too much, worry about whether this is disjoint from x or not. It need not be, because xh, this vertex may be this, this may be a neighbor here. So, this is, so in fact, x is always there, because you look at this vertex, this is already a neighbor, therefore, this will be an orange vertex. So, in fact, this xh has to be here, in fact, right, xh will be equal to x. So, x will also be part of them, but whatever it is, each of them will have a degree. See, dxi should be less than equal to d of x for I equal to 1 to h, any of each of them will be like that, right. Now, if you enumerate the degree sequence, all these numbers, that is d of x1, d of x2, d of x3, d up to d of xh, that means all of them will come before d of x itself, before or equal to d of x, because d of x itself is part of them. So, therefore, there are h numbers, there are h means d of x numbers which are of degree less than d of x. So, when actual d of x comes, it will be at least the hth number, right. This cannot be below h, d of x equal to h. This, when we write the number d of x here, that means that is h. So, already we are at the h position or even bigger. So, we can infer that d of x is less than equal to h. This is the point. This is a little tricky argument. What we have told is this, all that orange vertices on the path are such that they are non-adjacent to y. Therefore, the degree of those, any of those orange vertices plus degree of y should be less than the degree of x plus degree of y, because degree of x plus degree of y was maximized when that xy pair was selected, we would have taken otherwise those orange vertex and the y. So, it means that because d of y is same in both the sum. So, we can infer that the degree of each of the orange vertices have to be less than equal to the degree of x be h, then each of those numbers are less than equal to h. Now, in the degree sequence those numbers will get listed first, right, than before the degree of x is listed, that means that h degree of x equal to h is listed, right, all those numbers will get listed first. So, how many such numbers are there? There are at least h of them, because h orange vertices are there including x. So, h the number can be dx, right, or dx can come even after that, right. So, in the best case or the earliest case the d of x appears is as the hth number. So, there are many repeated h's, but at least I can say that then hth number has to be one of the h's. In fact, it cannot be greater, right. So, therefore, we will see that we will see that here we have an h and this is the h number. So, this number is less than equal to h. So, it means that the Chvatal's condition says, so in the graph the condition this d, the sequence d, d1, d2 etc. satisfies the Chvatal condition. Therefore, it tells us that we our d of yeah. So, it says that d of n minus h, this is essentially the dh number dh, this is h the number, right, dh is equal to d of x here, the h the number here. So, that happens to be dx. So, it is less than equal to h. So, now it is not that it has to be h, because it is, if there are many vertices which are of lesser degree, you can even have this less than strictly less than h, right. Then it means that d of n of h should be greater than equal to n minus h. So, it has to be greater than equal to n minus h. So, which means that there are at least h plus 1 vertices with degree n minus h or more, right, n minus h or more. There are which are those vertices? This is essentially corresponding to dn minus 1, dn minus h, these are h plus 1 of them are there. So, all these vertices will have degree at least n minus h, and our the vertex x has only degree h. So, it can be adjacent to only h vertices. Is it possible for it to be adjacent to all these h plus 1 vertices? So, there is definitely not possible, because it has only h neighbors, right. H plus 1 means this h, recall h is equal to d of x, right. So, we have d of x plus 1 vertices with degree at least n minus h. So, out of that our vertex can be adjacent to only h equal to d of x vertices. So, one vertex among them has to be, so let us say some z has to be such that it is not adjacent to x, right. So, it is not adjacent to h, but on the other hand its degree is at least n minus h, and this degree is h, d of x equal to h. Now, for this non-adjacent pair, if I considered d of x plus d of z, what will I get? I will get h for this, and here at least n minus h, that is greater than or equal to n. This is the point, but we know that this is wrong, because if this happens, if you consider the Hamiltonian path between x and z, we will have a red vertex and an orange vertex just side by side. So, that there is a connection here and there is a connection here, because together the set's neighbors cannot be placed without sitting on one of the, without taking one of these vertices which is just behind the neighbor of x, because we do not have enough, there are more than n of h neighbors of set, the h neighbors of x together they already make more than n minus 1, because there is n minus 1 places they have to find, in this n minus 1 places they have to, all of them have to find location, right. So, therefore, this will happen and then we will get Hamiltonian cycle. So, that is a contradiction, right. We are getting a Hamiltonian cycle, that is a contradiction. So, it means that, so if Chvatal's condition is satisfied for A, for every pointwise greater degree sequence, the corresponding graph has to be Hamiltonian. So, we have shown that. To summarize the proof, what we did is, if it is not true, we considered one such sequence corresponding to a graph with maximum number of edges among all possible such cases which violate our theorem that there will be a Hamiltonian cycle. And then among all the non-adjacent pairs, that is the key point, among all the non-adjacent pairs, because between non-adjacent pairs we already have a Hamiltonian path because of the maximality. Among all non-adjacent pair, we maximized dx plus dy, and then we saw that if it is maximum, and then applying Chvatal's condition, we can find a contradiction, because we will always have another pair dx and z, so the dx plus dz goes beyond that. That means it will already be n, and then it will be a violation. This is what we did. So, in the next class we will study the second part of Chvatal's theorem, namely if it is a Hamiltonian path, this condition should be satisfied. In fact, all the so if it is a Hamiltonian sequence, so that means if this condition is not met, then we will find some pointwise greater sequence which is violating the theorem. So, that is what in the next class we will do, we will show an example. Thank you.